In the previous video, we looked at the context of streaming and how is that a different problem statement from the batch processing systems that we've seen before. In this video, we'll start taking a look at specifics of technologies that can actually help us out. So first up, we spoke about the streaming application stack, which has got a bunch of different things. One of the most important components there is how do you deal with the data that's actually streaming, and what do you use as a persistent store. So the concept of streaming itself comes from having events which are captured at the source systems be available to you in real time. So that's what is called as event streaming. Um, there are other kinds of streaming like we spoke about in the use cases like video streaming, etc. But event streaming is what's of interest. So let's focus specifically on this and what technologies are available for this. So event streaming is the act of capturing data in real time from various event sources. In the case of ETL, when we took a look at the different sourcing options for data, we talked about event sourcing as a pattern. Event sourcing was what was used for instance, the change data capture, right, which was looking at all the changes that were happening in the source tables and capturing all those changes continuously. So imagine if that data was not given to you as a file, but given to you continuously in a stream, and that becomes basically like an event stream, as an example. Great. So, what constitutes event streaming? We spoke about that just now. But what is required for event streaming to be possible in the context of a streaming application? You would need firstly the ability to, not just capture the data in real time, but also store it, right? And that's the persistent store software. And usually, you need the ability to be able to go back in time and rewind and play back and things like that. We spoke about that in the streaming context. So the retrieval of that data from that particular persistent store needs to be possible at a later point in time. Most cases, uh, the later point in time usually happens immediately. But in some cases, like for instance, failure, fault tolerance, recovery, and stuff like that, it happens after a period of time, like maybe a couple of hours or days or whatever. So the third aspect of event streaming is to be able to then, once you retrieve it, the events, to be able to then manipulate, process it, and then take some appropriate actions based on that. Sometimes you might find that you need to look at multiple, periods of time of data, not just the most recent time. In which case, you might even go back and take actions for data that's already passed. So that's what is meant by retrospective actions. So that's also possible. Then finally, as and when the events become available from the source system and then get captured and stored, there could be many consumers of that data as is, right, without manipulation, without processing, and sometimes with processing, doesn't matter. But various different types of consumers, which have their own, different types of consumption patterns, could be requiring access to it. So that's also part of the event streaming capability that you need. So we will talk about what constitutes event streaming in the context of two different sets of technologies. One in the world of Google Cloud, which is one of the examples of public cloud technologies that you have available for event streaming, and then in the next week we'll talk about in the case of open source, which is much more widely prevalent and available across multiple different cloud vendors, including Google Cloud as well. So the combination of technologies that we will spend a lot of time on would be the persistent store software and the stream processing software. Right? These two things are foundational pieces of software that gets provided by various different technologies. But what is required for the application to get its job done will be a combination of these two and the definition of state and the definition of the processing logic that the application needs. So that is usually very application specific. So we're not going to spend time on that in this course. But you will get to see examples of this in this week's assignment as well as in the assignments that follow afterward. And obviously, the hardware is not something that we will focus too much on because we're going to do it on the cloud. And on the cloud, we will use the platform as a service options. So we don't need to deal with configuring hardware specifically. Okay. So let's first take a look at what what is one of the components of the stream processing that we're talking about, which is the persistent store software. In most cases, this actually comes down to a type of technology that's called as a message bus or a message service or a message queue, um, or an enterprise bus. So a lot of different variations of terminologies, but effectively they all mean the same thing. So what does the message service do? What does the message bus do? So let's take a look at a typical e-commerce application. Um, and using this example, we will understand what actually happens. So a user of the e-commerce service, uh, he logs in, like for instance, the shoe example that we spoke about with Flipkart, right? So the user logs in, places the order for the shoe. Now the shoe order has to be packaged, and that packaging has to be done with some kind of a backend workflow. That's what this arrow indicates. I mean, this gear indicates, flywheel indicates. So once the packaging is done, then the logistics company, which is responsible for delivering the package to you, gets notified, and then the delivery package, the delivery company then sends out the delivery truck on its beat, and then once it comes close to your house, then you get a notification for it, and then you open the door and receive the package, right? And this is like a very simplistic view. There are lots of other things going on, like for instance payments and refunds and stuff like that. Let's just focus on this though. So for this to happen successfully, there are lots of interactions that need to happen, right? Like for instance, the user clicking on the website to make the payment has to trigger a bunch of things, right? First trigger the package triggers the logistics triggers the route planning, the route planning triggers the notification to you when they come close to you, when the route comes close to your house, etc. Now, the role of a message bus is to completely decouple these kinds of systems. Why is that required? Because that um, allows you to actually build each of these different capabilities in a way that does not have to worry about how does this impact these other systems. So it introduces basically a decoupling of these different systems that allows you to independently build and test and scale the respective services. So, as an example, if the e-commerce platform or the website sends the notification to the packaging service, but for some reason the packaging service fails in the middle of doing something, then the ability to replay, the ability to do that packaging again, comes down to whether you can talk to that website and again get that same information, which might or might not be possible based on the design of the website, because the website itself is not doing anything on its own. If you notice, right, it's the user who's actually clicking through. So when this message that comes to the packaging service to say package the shoe, if that messaging fails or if that service fails, you can't really go back to the user and say, hey, can you click again, right? That makes no sense. Likewise, for the packaging service to go tell the logistics person, a logistics provider, which is usually an outsourced company, that I'm ready, pick up the service or pick up the package rather, means that these two have to be tightly coupled. They need to know each other. But tomorrow, if you change your logistics provider because you're not happy with the service that this outsourced provider provides you, then you're potentially forcing the packaging services outbound messages to be aware of what is the new vendor that you've chosen here, which could be problematic. Then the notifications, likewise, could be having its own vendor, and that needs to have its own, mechanism to relay back the messages back to the customer. So those kinds of things are there. Now, if you instead have a message bus or a message service, then that becomes the via media through which the data gets exchanged. Then, in which case, because you're organized based on events, and the successful completion of an event kicks off the next sequence of activities or the workflows that happen, you could think about capturing the events that are important for you in a common message service, which gets relied upon by everybody else, right? So, in this way, the e-commerce website is purely and solely dependent on only one different service which is downstream, which is a message service. It doesn't have to deal with the packaging service and its failures, its availability, etc., etc. And what's more important is that it's quickly doing its work, whatever work it's supposed to do, which is basically ordering, and then hands it off to downstream consumers to do their own thing. So this follows the hot potato principle, right? So for instance, as soon as the order is placed by the user, the message that the order is placed in the message bus or the message service, and then it's done. The acknowledgement comes back, then it knows basically, it's got the guarantee that the rest of the services will pick it up. Now, it might pick it up immediately, it might pick it up after it's recovered from a failure, whatever, doesn't matter. But it's got the guarantee that the services will actually do their job. That allows the e-commerce website to respond back to the user to say, look, I've acknowledged your order. You don't need to worry about it. Right? So this decoupling allows for faster response times back to the user. And more importantly, it allows for these systems to be completely independently implemented, independently tested, and what's more, independently scaled as well. Right? The e-commerce website is actually a very low cost website compared to the very low cost operation compared to the job of actually packaging, because the packaging act of packaging requires people to come in and assemble the inventory and tape it up and etc etc. So if you had tight coupling, like is the case without the message service, you would need to worry about how do I scale this? How do I get the response back? Like how many people need to be deployed in the packaging service so that my e-commerce website is not blocked. Whereas with the message service in between, right, the e-commerce website does its own thing, like we spoke about, and then the packaging service can be independently scaled. Like for instance, you have a festive season and you've got a whole bunch of orders which are like let's say 10 times more than what you would normally get. Then you can simply deal with it by having more people be deployed only for the temporary duration, so that all the packaging happens much faster. Right? And then once the packaging is done, it publishes back to the message service, and then the logistics service will get notified based on that, etc., etc. So this way, you can change your logistics provider, and absolutely nothing else needs to change. Right? So it's easy for you to deal with units of change and test it out, roll it out, scale it out, etc. So the message service plays a very critical role. Now, if you didn't have to deal with scale, if you didn't run a very popular website like Flipkart, if you ran a very small website which just has 100 users on a regular basis, this message service is like overkill. And for that matter, in fact, all of these different things can be tracked like in an Excel sheet, right? Because it's a small scale system and a human can do it. These technologies play a role obviously because the scale is large and it's impossible for a human to keep track. All right, so there are two of many messaging technology options, right? The first that we will take a look at is Google PubSub, which is part of the Google Cloud. PubSub is actually the name. Pub stands for publish, sub stands for subscribe, and we'll talk about that in a minute. And then the second one, which is the most popular open source technology in this space, is Apache Kafka. So what is PubSub? PubSub is a many-to-many asynchronous messaging service. Messaging service is exactly what we spoke about with that example. Asynchronous refers to the fact that two different types of users onto that same messaging service need not know about each other. Meaning, I could produce data and publish it to the messaging service. I need not know who else is publishing. I, in fact, need not even know who is consuming my data. The messaging service takes care of it. That's what it means. That's what is meant by asynchronous. The other thing is many to many, meaning I could produce once, and there could be many consumers of that data, and I don't care as a publisher. Right? The messaging service takes care of it. Likewise, the messaging service could be catering to multiple different publishers at the same time. Doesn't matter. Like it scales gracefully. It allows independent publishing to happen without having to worry about anybody else. That's what many to many refers to. Then the advantage, like we spoke about before, is it decouples the services that produce the events from the services that process and from the services that consume the events. And this allows for completely independent scaling based on the characteristics of the application that you're building. So the core terminologies associated with PubSub, first and foremost, is the concept of a message. A message is basically something that encapsulates an event. So you could call it data. Data is like the most generic term. You could call it event. Event talks about something specific, like for instance, the state associated with a particular business process. That's an event, and the change in the state is actually an event. So in general, though, at the level on which the message service operates, it's a message. The message could have multiple different types of payload. Sometimes you can also embed binary data sets and so on and so forth. Doesn't matter, right? Message is the unit of the operation, a unit of data that's inside the pops up. A topic is basically um, a way to refer to a bunch of messages, a way to refer to a feed of messages. So, for instance, if you take a look at that order taking website, the order taking website has to publish to the PubSub. When it publishes to the PubSub, it is made to use a topic which talks about orders. So the topic could itself be called as orders, and each message is basically a unique order. That topic of orders is not something that would be published into by the other publishers like the packaging service when it's ready or the logistics provider when it's ready to deliver, etc. Because those are completely different contexts. They might have, rather, they will have their own topics, right? That's good design. So the packaging service will have its own topic, which is called as, let's say, package status, as an example. Logistics will have its own. So a topic is basically a collection of messages, and within a topic, the messages are ordered by time. Meaning, I publish again, which means the second time I publish is necessarily available to any consumer only after the first message is also available. So there's an ordering to the way the messages are stored in the topic and as well as retrieved by any consumer. How does a consumer consume the messages from a topic? By signing up for what is called as a subscription. A subscription is basically some way of recognizing the fact that here's a consumer and I'm going to consume messages from this topic. There could be multiple different subscriptions, and each subscription could be at its own frequency, at its own speed, at its own rate at which it processes the messages. Doesn't matter to the publisher, obviously. Doesn't matter even to the topic. Right? The topic is always going to be the same, which is an encapsulation of messages. Different subscriptions could be at different places. Publisher, like we spoke about, is also called a producer. It's the one that's responsible for creating the messages and sending it to the topic. Likewise, the subscriber is signing up to the subscription with the message service for a specific topic so that it can keep consuming the messages from that. So, if you put it all together, a publisher publishes a message into a topic. A topic has a collection of messages. It uses a message store internally within PubSub, and it allows multiple different types of consumers, which are subscribers, to sign up for a subscription, right? And as and when the subscription is signed up for against the topic, then the messages become available for the subscriber to read. And once it reads a message, it then acknowledges to the subscription that I've read the message. That allows the subscription to keep making progress and keep feeding the newer and newer messages that keep coming in. Notice that this entire thing is like a continuous system. Obviously, it could have breaks in between, but it's meant to allow the publisher to keep publishing and the subscriber to keep subscribing without there being any stop. Right? Obviously, at times the publisher could stop because the messages don't make sense. Like for instance, there may not be any orders during early mornings because the website necessarily does not take orders at that time, or there's genuinely no traffic. In which case, the subscriber is all done and it's not doing anything busy at all because there's no messages, there's no orders, right? Likewise, you could also have a system which is continuously on, like the factory setting, right, which has the IoT data. The IoT data, which is a sensor, just keeps coming. The subscriber has actually no stop at all, right? It just keeps consuming those messages. All right, so we spoke about the e-commerce example. So now let's break that down further. How do you model that with PubSub? So the order taking service is the website. The packaging service, of course, that's a different service, and then the shipping service is usually some kind of an outsourced provider. Each of them is most likely going to have some kind of a topic, right? And this is again what we would call as design. You would not put all of them in the same topic. That doesn't make sense. That's not good design at all. So each event is of a certain type. So therefore, you could just group it all together into its own topic. And for every topic, there is actually a subscription that's attached to it. The subscription is based on the need. So the order taking topic, which has a bunch of orders as individual messages, the subscriber, one of the subscribers would be the packaging service, obviously. The packaging service signs up with a subscription, which is the packaging subscription, to the orders, so that it keeps getting these messages and then it does its own thing, like which is basically packaging and keeping it ready. Likewise, there could also be a notification system, which is only solely responsible for alerting the user that, look, I've received your order, and here's an acknowledgement, here's a confirmation, here's the invoice. right? That can also be a subscription against the same order topic. This subscription for notification to the customer is completely independent of the subscription that is responsible for packaging, which means the subscription of notification could be consuming data much faster because all it's doing is just notifying, right? There is no human involved in the loop and it's machine to machine. The subscription, which is associated with the packaging, has its own speed because there is a human involved in the packaging service, and by the time they're done, and they might consume the next data much later, right? So these two could operate at completely different frequencies. It doesn't matter. Likewise, the packaging service has its own topic. It's responsible for keeping on populating that with packaging related information. That's in turn subscribed to by two different people, right? One is notification to the subscriber again. The second is the shipping service. The shipping service gets notified. Rather, the shipping service gets given these messages as and when the packaging service is ready, and then it does its own thing, right? Likewise, that's how these things split across. Now, in practice, it's one message service which is pops up, which is interfacing, but behind the scenes, it's actually multiple different topics, multiple different subscriptions, each having its own frequency of consumption, etc. Okay, so let's take a slightly more nuanced example. We spoke about how a topic has publishers and subscribers. You could also have a many-to-many scenario here associated with that same topic. So, for instance, you could have two different publishers publishing to the same topic, which has multiple different subscribers, each subscribing on its own to portions of the topic. So let's take a real world example, right, to make it easier. That Flipkart e-commerce website that we spoke about, in reality, it's not just one website, right? It's not just one web server thread. In reality, there are multiple web server threads because it's a very popular website. It's doing lots of things. It's handling multiple concurrent orders at the same time. So in reality, there will be multiple different server threads, each servicing its own e-commerce requests, that the orders that are being placed on its portion. And so, as far as the topic is concerned, as far as the pub sub is concerned, it's as though there are multiple publishers publishing at the same time. But notice that they're all taking orders at the same time. They're not doing different things. They're actually all taking orders. So, from a perspective of a topic within PubSub, the orders topic, which is a collection of the feed of orders, is now having multiple different publishers, one per server thread. That's at the front end. So, multiple publishers publishing to the same topic, right? Now, from this topic, there could be multiple subscribers as well. Why would that be practical? That's practical because the set of orders that come in could be very, very large, right? Could be voluminous. Like take, for instance, one of those end of season sales that Flipkart does, right? Or Flipkart days, I think it's what it's called. So in those days, the set of orders will come in to the tune of lakhs a day, in which case you can't just have one subscriber, which is one process thread, subscribing and reading and doing things with it, right? Because of the rate at which the orders are coming in is potentially much larger. So in those kinds of scenarios, you could organize yourself into multiple different subscribers and read. That's one way to go about it. Or you could have multiple different subscribers subscribing to the same subscription, which allows for these subscribers to independently make progress on the same data and treat them in parallel. So, okay, what does it mean? So the order topic will have data from A and data from B. So let's assume there are two orders coming in, A and B. So I have two subscriptions. Like one subscription is for the packaging service, and one subscription is for the notification service. Now the notification service is super fast because all it does is notify the customer. So in which case the act of sending the notification is actually a cheap operation and might not take much resource at all. So I could get by with just one service, one thread rather, one process that runs to make the notifications possible. So let's assume that's actually subscriber 3, which is sending notifications to the customer. Only one server process is enough, in which case that server process initiates its own subscription, like we spoke about before, and that subscription will get both the messages A and B, both the orders A and B, and it goes and notifies the respective customers who ordered A and B. But the packaging service, on the other hand, takes a lot longer to get things done because it's actually involving like humans in the loop. So in which case, the way the workflow is set up could be in such a way that there is multiple different server processes, each processing its own orders. But the number of orders are going to be the same to both these subscriptions, right? The number of orders is basically the number of orders in the topic, which is A and B in this case. I don't want A to be processed by multiple packaging services at the same time. Doesn't make sense. That's like repeating the order multiple times. But I do want to guarantee that all the orders are processed. I don't want to miss B at all because A is getting processed in one go. So what I do then is all the different server processes which are wanting to process the same order and wanting to consume in such a way they are independently making progress in parallel, but they're not missing data at all, can therefore subscribe to the same subscription. So that subscription will definitely give the data A and B again, like it did for subscription 2. But it's the subscription's responsibility to split which data is given to which subscriber based on who is actually making the request at a particular point in time. So in this case, it split the data A and B into two subscribers who are potentially operating in parallel, right? And therefore getting more work done. So this is what is meant by many to many. So multiple publishers to the same topic, multiple different subscriptions, and multiple subscribers to the same subscription as well. That's possible. So this allows you to scale like dramatically, right? Publishers can scale independently. The subscriptions can actually be many, and then the subscribers to the same subscription can actually be many as well. Okay, what kind of endpoints are supported? What kind of publishing is possible? So the typical publisher to a topic is going to be some kind of a web server, some kind of a service that allows the application code to be written. So it could be end user apps, right, which have their own front end, like which has like a mobile interface or a web interface that comes in through a server interface, and then the server interface has its own server process which is publishing to the topic. It could be IoT devices like we spoke about. That's one of the use cases that we saw in the first video in this week. That's also coming through some kind of an IoT server. In many cases, we've also seen direct protocols be possible, whereby it's directly publishing to the topic. That's also perfectly fine. Or it could be services within the cloud, right? Within GCP or outside, doesn't matter, right? It could be a hybrid scenario, doesn't matter. So all of these are publishing to the topic. The subscriptions can be one of many, right? In the most general sense, the subscription is being subscribed to by a consumer who's like a microservice, like a small service which does exactly one thing. Like think about Hot Potato again. They do exactly one thing and then they hand it off to the next service. That kind of a microservice could be hosted in a VM, like a virtual machine, a container. Could be one of the platform as a service options within Google Cloud, like App Engine, which allows you to run standalone applications. Could be a cloud function. Like Google Cloud Function is actually an example of a serverless platform as a service option. Remember serverless from the cloud discussions, cloud native discussions, right? So it's basically something which is very low latency, which is very lightweight and can be done in embarrassingly parallel fashion. So cloud functions can also be very good subscribers. That's in the most generic sense. But you could also have on-prem systems which are subscribing to it. You could also have databases subscribing to it. You could also have data processing systems. Like we'll speak about data flow later on in this week's lecture. Or we could also have Spark streaming, we could have Flink, variety of different complex event processing logics. Those kinds of software can subscribe to it and then populate a variety of different destination systems. Like, the state can be stored in a data warehouse or it can be in a database cache, etc., etc. So with that, I think we'll just take a pause on the introduction to PubSub. In the next video, we'll take a look at some of the more detailed characteristics of PubSub.